Okay, it's a pleasure to have Robert today as our speaker. I think most of the people here know you, but if they don't, I'll just
They
say
will.
that
They will now. They will after this.
I'm sure they will. So as you know, Robert is an expert in everything statistics, I think. Time series, Bayesian stats, you name it. He's also a professor at the Australian School of Business at UNSW since 2003, as far as I noticed. And you joined the UNSW in 1985 after several years at the University of Chicago, right?
Right.
Now, Robert has numerous publications and also was ranked at the top 10 Australian mathematicians. So you know, and also a big joker. So it's going to be interesting and funny. So, Robert, go for it.
I can't, Rafa's already smiling. I can't live up to that, but okay. So thank you very much for that. I have to leave at 4:30 because I've got this comedy appointment at somewhere else. No, just kidding. Caroline looks very, very serious. So this work is joint with David Genowin and David Knott. So I'm going to talk about variational Bayes based on a copula of a mixture of normals, so that so you've used I think you've used a lot of Bayesian methods, and Bayesian methods have become quite popular, especially over the last few years for inference and prediction. And so that's sort of now, so there's a large number of applications. Now, the problem with pure Bayesian methods is that when you do MCMC, they're often quite slow, especially for models with latent variables and just models with a large number of parameters and models that are fairly complex. So approximate methods have been used, and in particular, one method that's quite popular is called variational methods, and in particular, variational Bayes methods. And those methods in particular, again, that are using Gaussian approximation to the posterior distribution. And so in variational Gaussian methods, you sort of assume that the posterior is normally distributed. You don't know its mean and its covariance matrix, but you know that it's normally, but you assume that it's normally distributed. And then you try to, by optimization, you try to estimate the parameters of this normal distribution, not by MCMC, but by optimization. Now, instead of assuming that, instead of assuming that the posterior is normally distributed, which it's unlikely to be, possibly it will be if the sample size is very large. Instead of assuming that, there's been some improvements where that assumption has been relaxed, and in particular, recently, Mike Smith and others have assumed that the approximation is a copula, and I'll discuss what that means exactly. There's also, when you assume that you've got a normal distribution for the posterior, and you've got, say, 10 parameters, then, and the posterior is approximately normal, then you've got 10 mean parameters to estimate and 55 parameters for the covariance matrix. So as well as assuming normality, you might want to actually simplify things and assume that the covariance matrix has some structure so that you're not optimizing over, say, 55 plus 10 parameters. So various approximations are made. And we look at an approximation based on a copula of a mixture of normals. Now, variational Bayes is an approximation to the posterior, and there are two uses that you can go along with this, two applications. One application is just to look at the posterior distribution and do some inference, like estimate the parameters or get credible intervals, posterior confidence intervals for the parameters. The other application is to do some prediction and get approximate prediction intervals. And I guess a third application is that we've actually used is when you've got lots of models, what you can do is you can use variational Bayes to select out of, say, 27 models, you might, or 100, you might select the top 4 or 5 and do it much more quickly than when you do margin likelihood. And then for those 4 or 5, you might do further selection by doing the whole Bayesian route by using a margin likelihood. And the way that you can do the model selection is to do cross-validation, and that sort of gives you one approach to model selection that variational Bayes is very good at doing. Now, the caveat in variational Bayes methods is that often the standard errors, the posterior standard errors, the posterior means are usually estimated quite well. The posterior standard errors are not estimated as well, are not as precise, not exactly what you get with pure Bayesian stuff like MCMC and Hamiltonian stuff, which is also pure Bayesian stuff. But variational methods seem to do well on prediction, or pretty well, and therefore they do well on cross-validation as well. And that goes back to model selection. So that's the interest. The interest is not just in pure estimation and inference, but also in terms of prediction and also in terms of model selection, so that if you have to pick between, say, 20 or 30 models, even if you could estimate one model and it takes you half a day or a day with pure Bayesian methods, when you get to having to estimate 50 of them for model selection, it gets a bit tedious and long, and then you might want to focus on a few of the better models, and then you either go with variational Bayes or you sort of then once you've narrowed it down to 2 or 3 models, you might then do pure Bayesian stuff. And that's what we did in another paper when we looked at cognitive science models and selected things with cross-validation. Okay, so we develop a variational approximation that's based on a copula of a mixture. And we use the natural gradient, and that's to make things, or at least an approximation to the natural gradient, in order to converge faster. So getting the natural gradient makes the whole method converge faster. And I'm going to illustrate it. We illustrate it in the paper. The paper is on arXiv. So I'm going to illustrate it using 4 examples. One is just the T distribution, multidimensional. One is a multimodal distribution. Then we've got a deep learning illustration as well. So the last illustration is for a Bayesian deep feedforward neural network regression. And each example, of course, because we selected it, shows that the variational approximation is more accurate than the corresponding Gaussian copula or a mixture of normals. So just the very beginning. So in Bayesian inference, we've got observations y1 to yn, and therefore we've got a likelihood that's p of y1 to yn given theta. That's the likelihood. The prior for theta is p of theta, and then we've got the margin likelihood on the bottom, the normalizing constant. That does not depend at all on theta. And on the bottom, we've got p of y1 to yn. That's the denominator is the margin likelihood. Now, in most problems, in all problems, but most problems, pi of theta is unknown. I mean, we can calculate it up to a normalizing constant, but what we often want to do is look at particular parameters, the distribution of particular parameters or combination of parameters. So even though we can calculate pi of theta up to a normalizing constant, the whole of it, it's very hard to actually look at the marginals for particular parameters or combinations of parameters. So for a long time, since the early 80s or the late 80s, we've concentrated on MCMC, one or other form of MCMC to give us some ideas about what's happening. And in variational Bayes, what we do instead of MCMC, so what in MCMC we set up a simulation process where we ultimately we generate samples after convergence, we generate samples from the posterior. Instead, in variational inference, we change the problem a little bit, and we say that, say, Q of lambda theta, well, lambda is, you can think of it as an index. So Q of lambda theta is our approximation to the posterior, to pi of theta, Q of lambda theta. And what we want to do is we want to minimize K L lambda over an index of posteriors. Thanks, Gilad. Over lambda is the index to the set of posterior densities, Q of lambda theta. You can think of lambda as an index, and you want to minimize that Kullback-Leibler divergence between them. So ultimately, just by itself, this would be a calculus and variation problem. But if we can write KL lambda in this way, so KL lambda is equal to minus script L lambda plus log of P of y1 to yn. Notice that the second term is the is the log of the marginal likelihood, and the first term is the elbow, is L of lambda is equal to the integral of log of pi over q by q. So to minimize KL lambda, we would want to maximize L of lambda over this index set, over the Q of lambdas, where lambda belongs to some index set. If we take Q of lambda theta, a parametric density for theta in lambda, then we would, for example, a normal distribution, then we would maximize over lambda. So instead of taking lambda as an index set, we say lambda is a set of parameters, and Q subscript lambda theta is a density, like a normal density. So then if Q of lambda theta is a normal density, then lambda would represent the parameters in the mean and the covariance matrix. And we optimize over that. So this turns, instead of MCMC, which is a simulation problem, this turns into an optimization problem where we try to maximize L of lambda, the elbow, we try to maximize over lambda. Now, that's quite difficult, but we can write L of lambda as an approximation, as an expectation. So this is L of lambda, script L of lambda is an expectation of log of pi over q with respect to q. So it's an expectation. And anytime we've got an expectation, we don't want to get disappointed. Anytime we get an expectation, we can estimate an expectation by drawing from Q of lambda. So we can approximate L of lambda by drawing, for a given lambda, we can draw from Q of theta from Q of lambda theta. And so that we can not compute, but we can estimate this expectation by drawing from Q of lambda. And if we can draw from Q of lambda, we can also, so we can draw, and we can actually estimate, we can differentiate with respect to lambda, and also, and if we can differentiate with respect to lambda, and let's go back to here, so we can differentiate inside the integral sign with respect to lambda, and we still get an expression for the integral, so we can get the derivatives of L of lambda, and therefore we can use stochastic gradient ascent. That's a method to maximize the variational lower bound. So we can get an estimate of the derivative because we can also express the derivative with respect to lambda as an expectation, and because of that, we can estimate it. So this is the first vector, first derivative of L of lambda, and we can actually estimate that, and therefore we can use an algorithm called stochastic gradient ascent in order to iterate towards the optimal, the maximum. Okay, so any questions at this point? Okay, so now, so the question up to this point, the question is, what should we take Q of lambda theta to be. And so one of the latest proposals is a Gaussian copula. So one of the things we can do is we can take the approximation, the Q of lambda, we can take it to be normally distributed. And if we take Q of lambda to be normally distributed, then we are estimating effectively the mean and the covariance matrix of a normal distribution. And if theta is, say, as I said, 10-dimensional, then there's 10 mean parameters and there's 55 parameters, distinct parameters in the covariance matrix. And of course, if theta is d-dimensional, where d could be 50, 100, or whatever, then you can see that there's d mean parameters and d plus 1 over 2 covariance parameters. So number of parameters that you have to estimate over becomes really large. So when doing Gaussian variational approximation, you want to think about how you can make that more parsimonious. Now, so that's a Gaussian variational approximation. So what is a copula, a Gaussian copula variational approximation? It's a Gaussian variational copula approximation says that basically you take each parameter and you transform it, like Box-Cox transformation or whatever, and then you assume that after transformation, the transform parameters are multivariate normal. So that's a Gaussian copula variational approximation. So if you assume things are normally distributed, then you're saying all the parameters have a joint normal distribution. So a copula is one step further than that. With a Gaussian copula, you transform the parameters. If you do a Box-Cox transformation, the transformation is easy. You just take a power of the parameter, you subtract 1, and divide by that power, and then you assume that after transformation, not only are the parameters normally distributed, but their joint distribution is normally distributed. And that's what, and that's could be a better assumption than taking things to be normally distributed. And Mike Smith and David and the co-author assume not so much Box-Cox transformation, but Johnson transformation, and also G and H family, which is a little bit better than Box-Cox, maybe a lot better. And they also, so after transformation, you get a normal distribution, but you still got this d plus 1 over 2 covariance matrix. So instead, they assume that the covariance matrix is given by effector model so as to cut down on the number of parameters. So what you do is you transform the T gamma. So you're transforming each parameter by this gamma 1 to gamma m if you've got n parameters. And then you've got the phi's then become the new set of parameters. And what we do is we transform, and then but instead of assuming a normal density, we are going to take a multivariate mixture of normals, and that's why I call it a copula of a mixture of normals. So you transform, then you take a mixture. Now, the reason this is reasonable, so then you get into why you do that. And so a copula is better than a Gaussian because it allows the marginals not to be normally distributed. It's still not very good. If you've got a multimodal distribution and you are using a copula, a Gaussian copula, then what you will find is that transforming to normality makes the multivariate normal approximation terrible because you're squeezing the modes by transforming the marginals. Now, if you take a copula of a mixture, it then becomes a universal approximation to any multivariate distribution, and you overcome problems associated with a Gaussian copula. The other thing you could do is take a mixture of normal copulas, but again, that's not a normal approximation. So we've taken something that is a good approximation, and we can show that it approximates any multivariate distribution, not in this paper though. And this is going to be our approximation to the posterior distribution. And then, of course, so we've taken, so this is now becomes our density, our posterior approximation for theta. It's a mixture of normals with k components, say. We still have to pick k. The weights are pi k, and the thing at the end, the t of gamma I dot, that's the Jacobian, because we're transforming from theta to phi. And then each component of the mixture of normals, mu k, sigma k, that's a mean, and that's the covariance matrix. And so now the variational parameters are the transformations of the marginals, the means mu1 to mu k of each component of the mixture, the pi's which sum to 1 but are the component weights, and then we've got the vecs, which are the diagonals and upper triangles of sigma 1 to sigma k. And these are the marginals for each of the phi I parameters. So we've got these marginals as well. These are what the marginals look like for the phi I. And we can show that this variational approximation, at least in principle, can fit multimodal, skewed, heavy-tailed, etc. distributions. And when theta is high dimensional, we follow a paper by David Knott and Mike, and we adopt the factor structure. So each sigma k is not a full matrix, but it's of the form. It's of the form. Each sigma k is beta k prime plus dk squared, where beta k is m by R matrix, which has a lot less elements than an m by m matrix, and the dk's are diagonal matrices. So there are two things that are at least two things that are important in the variational approximations. One of them is that that whatever you do, you want to be parsimonious. You don't want to have too many parameters, because if the dimension of theta is large, then the number of parameters actually can go quadratically, will go quadratically. Here, the number of parameters. Another one is the quality of the approximation in terms of being normal or being a copula, being a mixture. The number of factors can be different for each component of the mixture. So, and we usually take the first component of the mixture to be have more factors than the second, third, etc. And how do we implement this? We start off by fitting a single mixture component, that is a Gaussian copula, with a mixture of pi1, and then after optimization, we get lambda 1 star, the parameters for that, and then after we fitted k components, what we do to get the k plus first is we keep the lambda 1 star to lambda k star. Like for the second component, we keep lambda 1 and we optimize only over pi1, pi2 that sum to 1 and the second component parameters. So we don't re-optimize because that's too tedious, takes too long, doesn't converge well. So what we're doing is we're using a sort of form of boosting. We're doing boosting where we get the optimal solution for one component, we keep the parameters of that component, and then we optimize for the parameters of the second one, keeping the first component as we've optimized it, and then just estimating pi1 and pi2. Once we've got two components, we keep their optimal values and we optimize for the third, etc. And then we choose the optimal thing by looking at the lower bounds. So that at each stage, we're sort of boosting on, we are building on, say at stage 3, we're building on stage 1 and stage 2, and we're only ever estimating pi 3, mu 3, and beta 3, and d3. So that we're only optimizing on a small number of components. If we try to do everything each time, it takes far too long and it's not that stable. The mixing weights can vary, of course, and the parameter transformation and the transformations of the parameters we keep the same because we didn't find much advantage in re-estimating that. Now, we've got 4 examples that I'll switch over to in a second. The first example, so CMGVA is the Copula mixture of Gaussian variational approximations, is we try to approximate a high dimensional skewed and heavy tail distribution with the Copula mixture of normals. In the second example, we try to approximate a high dimensional multinomial distribution. With the third example, we approximate the posterior distribution of logistic and linear regressions, but I've got complex prior distributions. And the fourth example, we fit a Bayesian deep neural network regression model. So that's what we are doing. So that in the first example, we don't actually use a posterior distribution, because to see how these things work, we can just take any distribution pi of theta and see if we can approximate it. that'll do. And what we do is we take our target distribution is a multivariate T copula. It's not like a multivariate T, it's a multivariate T copula, and we see how well we do compared to, say, to a Gaussian copula or to a Gaussian. So basically, I won't say much more about it. The number of factors in the first component is set to 4, and then we take one factor for each additional sigma. So sigma 2 to sigma 20 is just one factor, and we're using 50 samples to estimate the gradients of the lower bound. So what we're doing is we are approximating the posterior, the target distribution, which is usually the posterior. We are approximating it by a copula of a Gaussian mixture, and we're comparing it to a Gaussian approximation, and we're also comparing it to a Gaussian copula. And so we compared it to Mike's algorithm, Mike and David Knott's stuff. And I'm gonna, at this stage, I'm gonna switch because something happened to the, I'm gonna switch, so bear with me for a minute and I'll be with you. Are there any questions at this stage?
Robert, I've got a question, maybe a silly one. Why copula work better than, let's say, you said a mixture model, right? So choose just a mixture model, do the regular variation Bayes. Why do you need to go through the copula?
Why does it? Well, number one, in the paper you will see, and I'll show that it works better than a mixture model. But let me explain it to you. Let me explain it to you a different way. Suppose that you've got suppose that you've got a bivariate example. You've got two components, and each of them is and are independent of each other, and each component is, say, a mixture of normals. And then now, do I want to do that? No, I don't want to do that. Let me switch, and then I will try to answer you. The reason is that if you've got the reason the copula might be better, not always, but the reason it might be better is that you are already transforming things to normality, and then you are fitting you're fitting the mixture rather than trying to fit the mixture directly to the parameters, which could be a complicated distribution. But that's not such a good answer. Let me switch, and then I'll try to answer it. Okay, so so the first, so let me so down here, so first of all, I talked about a natural gradient versus an ordinary gradient. So the lower, so this is the elbow, and this is the lower gradient. And this is the natural gradient, so that by using the natural gradient here, you're converging much faster. What you want to do is maximize this. You're converging much faster. Now, this is, these are the lower bounds for 2 components, 3 components, 4 up to 10 components. And actually 7, you don't get much improvement in lower bound after about 7 components. These are the marginal densities for second, third, etc., 20th component of theta. So the Gaussian copula is red, and the mixture of Gaussians copula is yellow. True density is blue. And you're doing pretty well with a Gaussian copula on the marginals compared to the mixture. However, when you look at the bivariate distributions of theta 1 and theta 2, you're going to get better approximations in the bivariate space for the copula of mixture of Gaussians than you are for the Gaussian copula. I'm going to take a second example, which is the, which is a mixture of 3 normals, and that's going to be a little bit multimodal. And what we've got is, we've got that basically after, I can't remember, 7 components or whatever, or 5, you're getting basically the best that you can with a mixture of normals. And these are, so here we've got that the true density for these various marginals, there's plenty of them, and so you've got the true density, the Gaussian copula, the copula of a mixture of normals with 10 components, and the mixture of normals again with 6 components that we chose by whatever reasonable method. And you can see that a Gaussian copula is unimodal and doesn't do as good a job as I think the mixture of normals or the copula of a mixture of normals. And this is essentially the same thing. And so now if we look at bivariate plots, bivariate plots, what you see is that this is the true dots. The blue are the dots coming from the true density, and then you've got the copula of a mixture of realizations from the copula of mixture of normals approximation. Whereas if you fit a Gaussian copula, then the overlap is a lot less with the true. So the Gaussian copula does not do a good job. Again, this would be for, this is another set of margins, marginal 30 and 50. What you've got is you've got the true versus the copula of a mixture of normals, gives you a much better overlap than if you're using a Gaussian copula. And now I'll go to the third example. Now, we took the priors to be of this form to get so that the density of the prior looked something like this, which was pretty stupid, but we stuck with it. The reason this is realistic, think of a slab and spike prior where you're doing variable selection, and one one component of the mixture is very thin, is very small in terms of its range, and the other component is large, and that's essentially a variable selection prior. And you'll get not this, but you'll get something, the same quality of thing. So here we've got a prior for the parameters that sort of gives you multimodality. And I mean, we chose it like that, but really a more convincing example would be something like a spike and slab prior. And then we've got logistic, the model itself is logistic regression or linear regression. And we applied it to 4 data sets, I think. And this is, so these are the lower bounds for this ionosphere data. This is a copula of a mixture of normals, the lower bound, and the mixture of normals lower bound is here, so that you're getting a better lower bound for the copula of a mixture of normals than for a mixture of normals. So this is just the empirical thing. I've still got to get back to Gillard. There'll be his Christmas present about the theoretical, more motivational reason. This is another data set where you see that the lower bound for the copula of a mixture is much higher than for a mixture of normals. This is a Bologna direct marketing data. So it works better, at least empirically, than a mixture of normals. And this is the flexible regression with deep neural nets, so that I won't go through all the neural net stuff, but this is what the data generated. This is the model. It's a deep neural net, flexible Bayesian regression. And what we want to do is get the posterior for this and look at the lower bound, plus also look at the partial predictive score to see which of a number of approximations does a better job. And again, we're using the 4 data sets of Bologna, direct marketing, etc. So here we've got, here we're comparing fitting on the posterior, the copula mixture of normals and the mixture of normals. And again, we're getting that the copula of mixture of normals gives you much higher lower bounds, or higher lower bounds anyway, than the mixture of normals. And the PPS values are also better, smaller, for a copula of a mixture of normals. And now in terms of the marginals, we've got a copula of a mixture versus a Gaussian copula now, comparison, and we're getting things that are different, and I think they're better as well for the copula of a mixture than, and you can check it out in the paper, than for a Gaussian copula. So let me just conclude. So Gaussian variational approximation says I'm going to take some if the variational approximation says I've got a posterior, I don't know what it is. I'm not going to do the full MCMC. I'm going to approximate the posterior by some parametric density. The question is, what parametric density am I going to use? And the simplest one would be a normal density. That's a Gaussian approximation. Something more sophisticated would be, let's first of all transform the parameters in some way, like Box-Cox. And then we fit a normal density to it. That's a Gaussian copula. What we've done is we've said, let's transform and then put a mixture of normals in, and that's a copula of a Gaussian mixture. Or you could just take a mixture of normals, and we've shown in these examples. And actually, you can probably and you can sort of argue more methodologically or theoretically or whatever that just the same as the copula, a Gaussian copula is often better than a Gaussian. You can argue that a copula of a mixture is better than just doing a mixture, and that's what. And then we've chosen the number of components in the mixture as by the lower bound. You can show that a copula of a Gaussian mixture is a universal approximation to a copula, to any sort of copula, and basically at this stage I will end it here and I'll open up for questions.
Thank you very much. It was really interesting. I've got a few questions, but I'll open up for other questions from anyone. I'll get the ball rolling, I guess. So one of the questions that I wanted to ask you was about the suboptimality, or if there is an issue of suboptimality by the way you add a component to the mixture every time.
Yeah. So basically, if you were fitting this to, so there's a lot that can be done. If you were fitting this to data, you would want to estimate everything at once. So what we do that's really suboptimal, but is number one, we figure out the transformation just by taking one component, of the parameters, rather than doing everything at once. So that we say, okay, we fit a copula and optimize over the transformation of the parameters. Maybe take the log of the parameters or something. The second thing is we to understand is the role of the boosting, rather than refitting everything, which makes it a little bit more unstable. Rather than fitting everything, we fit one component, we fix the parameters of that component, and then we fit the second component. And the only thing that we update are the things we update are the weights, which are now pi1 and pi2, but pi2 equals 1 minus pi1, and then the mean and the covariance matrix of the second component. Now, to go to the third component, we fix the means and variances of the first two normals, and we just update the weights, pi1, pi2, and pi3 equals 1 minus pi1 minus pi2. And then we also update the mean and covariance matrix for the third component. And we don't, so there's a lot of stuff that you can improve on. Maybe you can improve on in this. This is in the flavor of boosting, but it worked okay. The question is whether we can improve, whether that can be improved on it a lot. And I anticipate a question that I asked myself as well lately, which is, can we get on high dimensional examples, can we do better with normalizing flows, or what can we do with combining the two or whatever? So that, and again, I don't know the answer to that. you can do normalizing flows well in reasonable dimensions. The question is whether which approach scales up better in high dimensions. But yeah, you can sort of be more principled. I don't know if you do better, but you can be a lot more principled in the way that you do things.
So continue on that line. So when do you stop adding components? I guess maybe that's the reason you have to do it one at a time, because you don't know a priori how many components you should have.
When the lower bound stabilize, if I've got a lower bound and then I add another component and the lower bound does not increase, then I stop. So again, that's one of those things
how do you know that you do not overfeed?
I don't know. I'm just doing it by the lower bound. Okay. Now, another way to do it would be to actually do some cross-validation at each stage, because it's quick. So you could take 3 components, do a cross-validation score or whatever, and then do it, and then keep on going and select it in that way. And we haven't done it for a number of components. We've done it for different models. But so that's another way that you could possibly do it. So do I know that I overfit? I do it by the lower bound. I don't have a proof that that's not going to overfit or underfit or whatever. But I think that, so I think the issue of using copulas and using them smartly is an important one, because remember, what you want to do, it's a lot easier to attain normality of the posterior for each component than it is for the joint. I mean, and even so, you've got 10 components, and when you say the joint, you sort of say, suppose you take any 2 components, and then you the joint density. It's a lot harder getting the joint density of 2 components to be normal by transformation than it is each individual one. Suppose that you've got 2 components, and it's a bimodal distribution, for example, and then you transform each marginal to normality, and then so each marginal after transformation is normal, but when you look at the joint, it's going to be a mess, because basically by squeezing the multimodality out of the univariate components, which you can do just with inverse CDF, you're going to accentuate the multimodality and the horribleness of the bivariate distribution. So that you are transforming, but so you've got to consider transforming stuff, and basically, now you asked the question, let me try to answer your question as well. Now, suppose that you have a bivariate distribution, and you've got each marginal is it's a 5-component mixture of normals, right? Then then the bivariate distribution will have 25 components, right? If each marginal is 5-component, then the bivariate will have 25, and that's a lot of components lot of parameters to estimate if it's not like 2-dimensional, but it's 5-dimensional. Whereas if you can transform nicely, you might get away with 2 or 3 components. That's the reason for doing the transformation and taking and doing the copula. That by doing the copula, you might get a lot less components in the mixture than if you directly fitted a mixture of normals.
Okay, I'm convinced at the moment.
Well, just try it and think about it, because the question is, so univariate mixtures are nice, but once you get to if you've got a 5-dimensional parameter, if you're fitting a 5-dimensional mixture of normals, and each marginal is, say, 5-dimensional, then it's going to be 5 by 5, 125, 625. You're going to get like 5-dimensional mixture of normals, each with 5 components. How many components are you going to get in the multivariate mixture? It's going to be something like 3,000.
Okay.
I think. Anyway, so those are the building blocks, which are the copula of a mixture and the variational approximation.
Okay. Rafa?
Yeah, hi, Robert, thanks for the talk. I had some questions about this like approximation in the copula, because it looks like to me, I didn't know much about copulas, but I know some of the formulation looks like the normalizing flows formulation. I'm not sure if you heard about that. These are usually also transformations of a Gaussian distribution via some special type of neural network architecture that gives you invertible transformations. And then you train these invertible transformations by stochastic, like gradient descent as well. And it's in the formulation, at least it looks similar to the copulas. It's just that the copulas, they have specific parametric transformations that you guys are using, right? I think it was power transformations, right? When normalizing flows, they use some neural network to do that instead. But other than that, it looks very similar.
Okay.
I'm not, yeah. I was not sure if you guys thought about doing comparisons with these types of architectures. And there's also mixture density networks that are another type of neural network-based flexible distribution that is kind of like the other way around. You have a Gaussian, and the mean and covariance matrix of the Gaussian are given by neural network architectures. But they can also learn, we can also make mixtures of them and learn some flexible variation approximations.
Yeah, that would be quite interesting to look at and do the comparison. And I have no idea if it's probably not exactly the same. And the question is, how well do these things do, the normalizing flows, etc. So this would be something that I would be very interested in. So copulas are by no means just generally necessarily the best way of approximating densities. This is one way of doing the variational stuff, but I would be very interested in looking at the other stuff. I don't know about it, but I'd be very interested in looking at what people have done and comparing it with the stuff we've done.
Mm-hmm. Cool. Yeah, I think some of the advantages are probably the approximation, like the universal approximation properties that you guys get with the mixtures of copulas. I'm not sure if the normalizing flows have, at least not in general, maybe a few architectures perhaps is provable. And I'm not sure, perhaps you guys have a better fit because you have a flexible it's almost like a non-parametric thing, right? Because you can add components, right, to the mixture as you go, right? And
Yeah,
normalizations, they're fixed.
Why don't you, that would be good to discuss further, just to get, just to sort of see what people have done and where we can go with that. Now, another possibility is to sort of say, suppose that we take the two approaches that could be related. We could say, can we use one and then build up more by using the other one? So we're doing sort of boosting, right? We put one component in, then we add another one, and so on. Why can't we also discuss in a similar way, doing one approach and then starting a second approach to boost the first approach in some way?
Mm-hmm.
By adding whatever, so that whatever we can do to, I mean, the nice thing about the mixture of normals thing is that we can add very parsimonious, you know, you've got like 100 parameters. So and we've got 20 components. Now the 21st could be a vector of means, and then a vector of, and then a one factor model, so that you've got another 100 things in the vector, plus on the diagonal another 100. So you've got, say, you're only using 300 parameters to actually add a component. So there's lots of ways of, you know, because you don't want to use too many of these, because the number of parameters you're optimizing over starts growing a lot. So there's a, you know, we can use combinations of ideas to actually improve things. I haven't done it, but that could be there could be clever ways of, and actually the other thing is, if you want to get universal approximators for copulas, then I think that you can have that the first component has a mean. Well, if you're going to use copulas if you're going to use a copula of a mixture of normals as a universal approximator, the first component could have a mean and some covariance matrix that's a correlation matrix, and the rest of them can have zero mean and a one factor structure, and and then it'll also be a universal approximator but have many more components. And you can have all sorts of parsimony in there, and I'm not sure what the trade-off in terms of number of components versus number of parameters is. But you can picture you know, just a univariate normal approximation to a density, and you could say, I'm going to have the same variance parameter for the univariate density in the mixtures, but I'm going to have different means, and that's all that I'm going to have. And that will still be probably a very good approximation to a univariate density. In the same way, you can now start thinking of approximating multivariate copulas, or by various combinations of parsimonious components. I mean, when you think of it, it's what you're doing is you're transforming to something sensible, possibly sensible, and then you're just fitting mixtures, and you can fit mixtures in multivariate land in very many different ways. You can have the means all different, but the covariance matrix is the same, etc., etc. And I don't know what the optimal thing is, but there's a lot of choices. If you see what I mean.
Yeah, it sounds quite interesting.
So there's a lot of choices in what I think even on the univariate case, there's lots of choices, because you take a mixture of normals and you can take all the means different, but all the variances the same, and you can probably get a universal approximator to a density. It's just that you might be using a lot of components. You don't have to take the means and the variances in each component different from each other, potentially different. And you can still get universal approximators. Now, if you translate that into the multivariate space, then there's lots of choices you can do to get universal approximators that don't involve even different covariance matrices. Because all you're putting these little bits in that are located in different places. There's enough of them, then you are then you're covering the whole space. What you've got to watch out for in Copulas is that when you transform to something nice on the univariate level for each component, then you've got to allow for the fact that you can make the joint more complicated. And to assume that the joint is then a Gaussian is naive, and that spoils things. You might as well assume that it's a little bit more complicated once you've made the marginals really nice. If you see what I mean.
Yes. Yeah. Thanks.
So Rafa, if you're interested, let's talk about it. If you're not interested, give me those references anyway.
I'll send an email. Yeah.
Terrific. Yeah. So that's basically what. Now the next. And then there's all these things that are linked up to prediction, which nothing to do with Copulas, but to do with VB. Have you seen that stuff?
In terms of improving predictions?
In terms of good predictions from VB.
Yeah, like other methods that's like normalizing flows and these other effects, but
yeah, so you don't need to do good prediction. You don't need to get your high moments correct to do good prediction. Anyway, let's talk about it offline. All right, so that's it from me.
Robert, thank you very much. It was really interesting, and I think there's some use cases we can think of, especially the neural nets one that you're talking about. I think there's probably quite a bit of application for that. So again, thank you very much. It was really, really good. Thank you.